Welcome to clickmyproject.com.
Parallel augment Lagrangian relaxation method for transient stability constraint unit commitment. The problem of unit commitment involves finding the least cost dispatch of available generation resources to meet the electrical load. The unit commitment problem in a power system involves determining the startup and shutdown schedules of thermal units to be used to meet the forecasted demand over a future short-term 24 to 168 hours period. The objective is to minimize the total production cost while observing a large set of operating constraints. The unit commitment problem is a complex mathematical optimization problem with both integer and continuous variables. Generating resources can include a wide range of types: nuclear, thermal, renewables. The key decision variables that are decided by the computer program are generation level, number of generating units on the later decision, are binary 0 or 1, which means the mathematical problem is not continuous. In addition, generating plant are subjected to a number of complex technical constraints, including minimum stable operating level, maximum rate of ramping up or down, minimum time period the unit is up and down or down. These constraints are amenable to mathematical programming as linear or mixed integer constraint. We present a transient stability constraint unit commitment model which achieves the objective of maintaining both transient stability and economical operation. In order to solve the transient stability constraint unit commitment problem, augmented Lagrangian relaxation combined with variable duplication techniques and the auxiliary problem principle is used to decompose the transient stability constraint unit commitment problem into two subproblems. One subproblem is traditional unit commitment problem with prevailing constraints. Another subproblem is modeled as a transient stability constraint optimal power flow problem. The first subproblem is solved by dynamic programming, while the second subproblem is solved using a reduced space interior point method. In augmented Lagrangian relaxation, an efficient hybrid subgradient method is developed to update all the Lagrangian multipliers. The iterative process continues until the duality gap is sufficiently small. This is the flow of our project consists of 5 modules: unit commitment problem, dynamic programming, predictive alternative point method, parallel implementation, and performance simulation. In the unit commitment problem, we have some few generators units. Also, we have some forecaster load. Besides the cost of running the units, we have the additional costs and constraints: startup costs, shutdown costs, spinning reserve, ramp up time, and more. It turns out that we cannot just flip the switch of certain units and use them. We need to think ahead and based on the forecasted load and unit constraint, correspondingly here displayed here. This is the maximum generating units of megawatts of generator, and this is the load. Second row is the load. I calculate the commitment of the generator for 12 hours. This is the hourly results based on the new loads. Here is displayed here. From this I conclude that our proposed method performs better than existing methods.